Hi everyone, welcome back to my math teaching channel online again. So today I will get into another sketching function, and this function is a lot more complicated than the other one we did. So let's get right into the question. So we have a rational function f of x equals x divided by x to the power 3 minus 1. Now, if you remember the sketching of Math 12 in the previous course, right? When we have a rational function, we have to look at vertical asymptote and horizontal asymptote. And why do we have to do that? Because we want to know is our function is discontinuity or continuous, and is there any point the function is not exist, the y value does not exist, right? Because it's rational function. Now we know that we don't allow for denominator equals 0. So we have a 5 over 0, that's not good. We have 100 over 0, not good. But if we have a minus 6, 0 over minus 6, that's okay, right? So as long as our fraction doesn't have a denominator is 0, then it's fine. Now, that is a numerical value. However, because our x is invariable, and therefore we don't know whether or not this expression make any value of x make this expression become 0. The bottom becomes 0. And we want to avoid that, right? And if this bottom becomes 0, we don't want 1 over 0, right? This is not except, right? And if we have that happen, if this bottom becomes 0, it means at that point, the y value does not exist, right? So we want to find out, and we call it the vertical asymptote. So the way we find the vertical asymptote is we set the bottom equal 0. And we want to find out what the value of x approach to make the y become, the function become does not exist at that point. So let's check, right? So I'm going to say x3 minus 1 equals 0. I'm going to set that equals 0. And solve for I can see what value of x make this expression become 0. So move it over. You have x3 equal 1. So it means as long as x equal 1, then the whole thing here becomes 0. And this is true. 1 minus 1, 0, right? So therefore, this becomes our vertical asymptote. So we know we have a vertical asymptote at x equal minus 1. Okay? So let me explain the vertical asymptote. So let's say if you have a coordinate, and let's say this is the vertical asymptote. At this value, x1, you have a vertical asymptote like that, right? So that is about vertical asymptote. But we also have to look for the horizontal asymptote. Maybe we also have a horizontal asymptote right here, or down here, or right above the x-axis. It's like this, or right the x-axis, right? So we want to check that as well. So now we check for horizontal asymptote. And to check the horizontal asymptote, we usually find out the behavior function when x approach to positive infinity very far on this end, and very far on this end, negative infinity, to see where the y value go, right? If the y value at that point approach to 0, which is this y equals 0, which is this number line, then that is our horizontal asymptote. So let's take a look at that. And to do that, we have to take limit, right? Limit of this function, x over x power 3 minus 1, when x approach to negative infinity. And we know that we can factor out this x down here, square minus 1 over x, right? And we can cancel the x with the x here, so this becomes 1. So what happened when we substitute this value in? We have 1 minus negative infinity. This fraction will approach to 0, right? But if this number down here is very big, 1 divided by big number equals 0, right? Approach to 0. So we have left with this. It means our horizontal asymptote will be equal 0, but slightly on the left, right? Negative, because we divide by negative infinity. The same, we're going to take the limit when x approach to the right-hand limit and see what happens. When x approach to positive infinity, the scenario will be similar, however, will be like that, right? Therefore, we have a 0 slightly on the right. So now we know like our horizontal asymptote is what? Y equals 0. Because limit of it is 0. Left-hand limit equals right-hand limit, right? Equals 0. And the horizontal asymptote is y equals 0. The vertical asymptote is x equals 1, which is right here. The horizontal asymptote is y equals 0, which is right here. Okay? So now, what else do we have to do in terms of the limit? Whenever we have a vertical asymptote, we want to find out our function behavior. Do we put the pen down here to draw it? Or do we put up here to draw it? Or we put down here to draw it? So we look at the vertical asymptote when x approach to 1, slightly on the left, and when x approach to 1, slightly on the right-hand side. So again, we have to take the limit of this function when x approach to 1 on the left. And the way we evaluate, we're going to use exactly the function just to put in the value, right? So that slightly less than 1 will be 0.999 over 0.999 power 3 minus 1. And when I put this value in our calculator, I got the answer minus 333.33. Now this considered like a big number, but negative infinity. So now we know when x approach to 1 on the left, our y behavior approach to negative infinity. Now we do the same, take limit when x approach to slightly 1 on the right-hand side, right? 1 on the right-hand side. We will have the same thing happen, but this time we substitute by 1.001, slightly more than 1 a little bit on the right-hand side, divide by 1.001 power 3 minus 1, we will get exactly the same value, except this is positive. So this is the same like positive infinity. So now we know if x approach to 1 on the right-hand side, our function will approach to positive infinity, our y function. So up here somewhere. So now, let's look at what else. Okay, so we analyze the limit of the function, and we realize that we have one vertical asymptote at x equals 1, right? This is the vertical asymptote, and one horizontal asymptote at y equals 0. So now, at this point, we can move on and do the first derivative, right? So the first derivative, y prime, I will take the quotient rule, use the quotient rule, we keep the bottom the same, the denominator the same. Take derivative, first one is 1, we don't have to put in 1, minus, keep the numerator the same, time with the derivative of denominator, which is 3x squared, minus 0, constant, right? Now, the bottom is x to the power 3 minus 1, all of them squared. So, let's summarize the first derivative. We have x to the power 3 minus 1, see times that, minus 3x to the power 3. All of this over x to the power 3 minus 1 square. So at this point, we can set this function equal 0 to solve for Reticle points. Remember the previous lesson, right? So we're going to solve for the Reticle point here. And how do we solve for Reticle point? Remember, this is a fraction. But let me simplify this numerator first, okay? So this will become minus 2x to the power 3 minus 1, because this, we subtract this, right? All of this over x to the power 3 minus 1, all of this to the power 2. Now, if we set the numerator equal 0, so it doesn't matter what denominator is, right? What is our denominator is. We just set the numerator equal 0. The left side will equal the right side. So therefore, we just solve for x based on the numerator, right? So minus 2x to the power 3 minus 1 equals 0. Move it over, minus 2x to the power 3 equal positive 1. Divide both sides by minus 2x to the power 3 equal third root of minus 1/2. And therefore, x1 equal x2 equal x3 equal minus 0.79. So that's the root of our function for this value, right? So that is the Reticle point. So we have one Reticle point at 0 minus 0.79. So now let's move to the next board, and we're going to do the second derivative for the next bar. Okay. So let's watch the next bar. So now I'm going to take the second derivative. What is the second derivative based on this one, right? So based on the first derivative. So keep the numerator the same. X to the power 3 minus 1 on of this square, keep the same. Derivative this one minus 6 x squared minus 0, we don't have to do that, minus, now keep this the same, so minus 2x to the power 3 minus 1, keep the same. Derivative of the denominator, bring this in front, so times 2 times with x to the power 3 minus 1 to the power 1, right? And then don't forget chain rule, times with 3x squared. Okay, so now all of this will be equal x to the power 3 minus 1 and become power 4. So at this point, this is a complicated function. I'm going to show you how to simplify this function. So don't bother to expand this and tie them together. That will be too complicated. So what we should do here, we should look at for the common factor, right? This term is x to the power 3 minus 1. This term is x to the power 3 minus 1. So this becomes our common factor. And we're going to choose the least power, which is x to the power 3. We pull it out. This is our common factor. And the least power is power 1. We take this power. Inside, we're going to time with minus 6x squared and also time with one of this, because we have power 2, we need one of this more. So x3, x to the power 3 minus 1 more of them. Minus, put that side down. We have this one, so we're going to put it in minus 2x to the power 3 minus 1. 2 times 3 is 6x squared, and this one we already have it here, so we don't have to bother to put in. So that's how we use general common factor, and we pull out the factor and we do whatever inside here. Okay, underneath this we have x to the power 3 minus 1, all of them to the power 4. Now you can figure out, this is the multiply bracket together. So it means we allowed to cancel the same term. And this will reduce to down to power 3, right? And this gone. So at this time, simplify one more. We have minus 6x squared. Let's multiply through, okay? So minus 6 times x will become minus 6x to the power 5 minus 6x squared. And minus times minus is plus. Now this one, we change whatever the sign here, but we're going to time this with this, right? So 6 times 2 is 12, and that should be minus. However, because it's negative sign, so it should be plus 12x to the power 5. And this time this will be minus, but because the sign, so become plus as well, 6x squared. All of this over the same denominator. Now we're going to simplify one more time. Minus 6x5, adding with 12 is 6x5, so it becomes 6x to the power 5. Plus 6x squared plus 6x squared become plus 12x squared. All of this over this denominator, x to the power 3 minus 1, all of this to the power 3. So at this point, we know this is our second derivative after we simplify it. You can see the long way, but it becomes very short, right? So that's not bad, but let's see how we're going to deal with the critical point. So at this point, I'm going to set the second derivative become 0 to solve for the inflection point, okay? Over x to the power 3 minus 1, all of this power 3. Again, we just care about the numerator, right? The denominator doesn't matter, okay? As long as the top one equals 0, everything becomes 0. So left side and right side. So now let's solve for x. So I'm going to factor out the top. So 6x squared times with x to the power 3 plus 2, right, equal 0. So that tells us that x will be equal 0 because this one equals 0. The first bracket, the second bracket will give us x to the power 3 equal minus 2. And we take the third root of it to get down to x. So the third root of minus 2, x will be equal, x1 equal x2 equal x3 will be equal minus 1.3. Okay, so this is the inflection point. Inflection, and this value here is the critical point. So from the first derivative, we solve for critical point. From the second derivative, we solve for the inflection point, right? So we got inflection point is minus 1.3, and we got critical point is minus 0.79. Now let's move on to the data table analysis. For the next board, I am going to collect the critical point and any point across for the x, put in this table. So let's say this is negative infinity, and then we have, now we do have x equals 0, right? Because if we set the x equals 0 here, this function is perfectly work well. So if x is 0, y also is 0 because the top is 0, right? So this y function. So we know that x can be 0 as well, but let's put minus 0.79 and then come to 0. And then what is the next one? Minus 1.3, right? Okay. So I'm not sure is it minus 1.3 or minus 1.2. Let me check third root. Not sure. Okay, so math to root, go down to number 4, then minus 2. We got minus 1.25, which you draw off become minus 1.3. Yeah, that's correct. Okay, so now let's put in the interval and let's put in our derivative. So what is our derivative? Y prime, right? This is Y prime, first derivative. Equal what? Equal this one, right? So minus 2 x to the power 3 minus 1 on the top. At the bottom, x to the power 3 minus 1. All of this is square outside. So now what is our Y prime? Y prime is this one right here, right? This one down here. Okay, so I'm going to put it in and I will show you later. So you see our Y prime equals 6x to the power 5 plus 12x squared. All of this over x to the power 3 minus 1, all of this to power 3. Okay, so now let's choose the testing point. So let's look back here. Now let's choose the testing point. Between negative infinity and negative 0.79, then our testing point will be minus 1. Okay? Between this and this, our testing point, we can choose minus 0.5, right? Our testing point. Between this interval 0 to minus 1.3, we can choose our testing point is what? Minus, oh, I forget. Sorry about that. I should put this number in front of this. Oh, sorry for my silly mistake. Okay, so this is minus 1.3, suppose load first, then minus 0.79, and then 0. So now, between this and this number, we can choose minus 2 as a testing point. Between this and this, we can choose what? Minus 1, yes, correct. Minus 1. Between this and this, we can choose minus 0.5, right? Everything else here, as long as it's x not 1, x can be 2 or 3 or 4, whatever you want to do, okay? Now, let's choose and see how this look like. We're going to put in here. If we put minus 2 in the top, so minus 2 become minus 8. Minus 8 times minus 2, which is positive 16 minus 1. So the top become positive sign, right? Down here, it doesn't matter. This is negative. As long as you have a square outside of anything inside here, this function going to be positive anyway. So positive divided by positive. And positive divided by positive, of course, the answer will be positive, right? Now let's check this one. Minus 1, if we put in here, it's minus 1 times this is positive 2, minus 1, so that also positive. Down here is only positive, so divide, it will be positive as well. Minus 0.5, put in here. Okay, let's check how it look like. So minus 0.5 to the power 3. Minus 0.5 to the power 3. And time with minus 2. And minus 1. So you get minus side, minus 0.75. So this is minus. And down here is, of course, positive. So this divide will give us negative value. Now 2 put in here. So 2 put in here is become negative. Negative 8 times 2, negative 16, minus 1, minus 17. So this is minus divided by positive down here. So this will also become negative. So let's analyze how the function look like. If you have a positive sign, which is the function y or function f of x, will be increasing. So I put the arrow right there, okay? So this function will be increasing. If this one is the same, so f of x will be increasing because the positive side. Negative side, so f of x will be decreasing. Negative, decreasing. So the arrow show the function intervals, right? Up and down, increasing and decreasing. Let's check this one. And this one, we're going to analyze concave, right? Concave pattern. So if we put -2 in here, this become big minus, adding with 48 become minus, yeah. So that would be positive. No, -2 in here, so -32 times 6, because that's so negative, sorry, negative. And down here, because we have a power 3, so this will become a negative, and power 3 is so still negative. So negative divided by negative equal positive. -1 if we put in here, so it become -6. -6 times adding with 12, so it become positive. -1 put in here, minus, so minus. So that also become negative, right? Positive divided by negative. Yeah. So minus 0.5, let's do that. Minus 0.5 to the power of 5 times with 6, minus 6, adding with 6, right? Adding with 12 times with 0.5 square. Okay, so that number become positive as well. Positive. Okay. Try again. Minus 0.5 to power 5. We minus times with 6. We negative. Adding with 12 times 0.25. Yeah, it's positive. Divided by minus 0.5. Put in here is minus. To power 3 is minus. So that's also become minus. 2 positive, put in here, everything up here positive. Down here, 8 minus 1 will be winning, so it's 7. So positive. So positive divided positive is positive. So that's our side for the concave. Now what it look like? We'll have concave up, right? Because positive. This negative, so concave down. This negative, concave down. This positive, concave up. So what's this function look like? Concave up look like this, and we have inflection point at this point, right? Our inflection point. So we have concave up, okay? Then we have an inflection point here, so concave down. So we have inflection point and then concave down. And then continue concave down, right? And then between concave down and concave up, we have another inflection point in here. That's down and then, concave down. Okay, so on the way concave down and then change into concave up. So concave down, concave up. So look like something like that, okay? So now when you sketch this function, I suggest to you, if you want to be accurate on of this critical point, you can find the y component of it, right? What I mean is, I have to erase some part of this, okay? What I mean is you have the critical point as -1, 3 as the value of x. coordinate. To find y coordinate, all what you do is substitute minus 1.3 in the original function, right? Like that. And calculate the y. Whatever the y here equal, you put in here, right? So then you have accurate point. So that's 1 point. Another point is 0, which is 0. Another point is what? Minus 0.679. And calculate the y again. Then you get a point, right? So mark this point and sketch the function. Now, because this is a long video, so I don't want to bother to go with you. I just show you the way you should calculate the point like that, right? So calculate the point like that and put in the y value and get the shape of the function. Now, I'm going to do the shortcut. Now, I strongly advise you using sketching by hand first. Follow the data table analysis, put on the coordinate. But then use the graphing calculator at the end, key in the function and check how the function look like. So I already key in the function here, let's drop it. So that is the function look like. So here look like the function across 0.00, and there's the inflection point and going down here. This is concave up. So it concave up, and then at about 0.79 minus 0.79, right? There is the inflection point going on here. So concave up, become concave down. Go to this one. Something like that, right? And then go down like this, right? So that's the anti-horizontal vertical asymptote. And we analyze the vertical asymptote from the left-hand side, limit a bit, and from the right-hand side, limit a bit. It seems that we're missing that one, but you know what I mean, right? So we can analyze when limit of this function x over x to the power 3 minus 1, when x approach to 1 on the left, and when x approach to 1 on the right. Then you get the limit will be on the left will be negative infinity, and on the right will be positive infinity. And that's why on the right-hand side, it goes like this. And get along with the horizontal asymptote and vertical asymptote. There's an inflection point going on here between these two functions. So up and then transition down. So that's just how it looks like, okay? And you might not see it because of the white spot. So I'm gonna move. I'm gonna turn off the light, see what happens. You still have the white spot there? No. So that's the shape of the function look like, right? Okay, so I end the long video here, our video here, and I hope you enjoy my long work. It's so boring, right? Because we have a lot of work going on, but at least I show you how to take derivative for the complicated function. And finally, we got the second derivative, simplify it. We got on the data value, we analyze the function. This is the main point I want to show you in this course for curve sketching function. And don't forget, we check it by using technology, but we don't want technology to replace math. You still have to know how to analyze the data, look at the interval of concave up, concave down, inflection point, blah, blah, blah. We have to find out. So all of this we must do by hand. And then after that, we can check and sketch the function to see our work. So that's the way we do math. Anyway, Thanks for watching for a long lesson. And see you in the next question. Now, the next video, I will get right into the application of extreme value, right? Now you know what is the minimum value and maxima value. We get into the application later. So you see, I organized the lesson by the sequence step 1 to step 2, step 3, and connect them logically, how I explain where the derivative come from, the limit. After we do limit, we learn derivative, and we learn application of derivative, and now we learn how to sketch the maximum function, minimum function level, so we can get into the application of extreme value of the maximum production level benefit, or minimum the production level for our costs involved for purchasing, whatever in finance, and a lot more in other application as well. So you will see. So stay tuned for the next video. Get right into the application of extreme value. And thank you for watching. Don't forget to give me a thumb to support my spirit and cheer me up for my hard work. Thank you. Bye for now, everyone.